guys, and welcome to another video. Today, as promised, I'm going to take you through derivatives, show you the different rules in terms of derivatives, give you some examples, and of course give you a bonus towards the end of the video. Please have your pen and paper ready because it will be very good for you to take down the rules. Also try to work out some of the examples that I give you and try to beat me to the answer. Pause the video, see if your answer is correct. So let's jump into it. So what is a derivative? So a derivative basically tells us the rate of change with respect to a certain value. Okay, so basically this means is it tells us how fast something changes, and we can, as an example, we can say that the temperature is dropping at 2 degrees per hour. So the rate of change, which is the temperature dropping per hour. This is indicated as d over dx of f of x, or we can write it as f prime of x. Okay, so you'll see both of these within the examples that I give you. We also say that the derivative is the slope of f of x. So basically it means that if we were to look at the Cartesian plane and we have our y and our x-axis here, and we say we have a horizontal line here at -2, we say that the slope here is equal to 0, or we'll say that f prime of x is equal to 0. So the derivative of -2 here is 0. Okay, so that's basically what the derivative is. It's the rate of change with respect to a certain value, or we can look at it as the slope of f of x. We can further look at this on the Cartesian plane with an example. So let's say we have f of x is equal to x squared. Now we know that with x squared, if we put this on the Cartesian plane, let's just draw the Cartesian plane quite quick. So we can say we have the y-axis, and then we have the x-axis here, right? So we'd say y is f of x is equal to x squared. Now at this point we don't know how to find the derivative, but we know that x squared is the hyperbola of this. So it's not too accurate, but it's basically looks something like that. Let me actually draw that a bit better. We can draw it like this. Must make contact at 0. So that's the hyperbola we get with x squared. So if we want to find the derivative, we can find the derivative of both sides of this. And if we are to look at it, we look at the tangent line. So the tangent line is basically the line that cuts x squared at one point only. So if we have something here, let's say we have a line here, and we can say that this is a high slope. Okay, if we have another point here, we can say this is a low slope. Okay, and it's the same if we have a line passing through here. This will be a low slope, and that will be more of a high slope. Okay, and we can see that, right? We can see where it's cutting the graph of x squared, and we can see that it is a low slope and a high slope. Visually see it, right? If it cuts here at 0, we know that the slope here is equal to 0. Okay, so what we basically have is we have positive slope here, and we have negative slopes here. Okay, because we're on the negative x-axis and positive x-axis. Okay, so quite simple, quite important just to understand it from a graphical point of view, because going forward we'll mainly be using the derivatives, and I'll show you how to actually do this using different types of rules. So let's jump into the next part that I want to show you, and that is basically what some people call the definition of a derivative. So definition of a derivative. And I know I did speak about the what is a derivative, but in mathematical terms, the definition of a derivative is represented as f prime x, which is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, right? So just take note of this formula, because we will be using it in some of the examples that we are going to look at next. Okay, so like always, let's jump into the rules. So let's go into the rules. Let's have your pen and paper ready. So I'm going to take you through all of the rules, write them down, keep them with you, but always ensure that you don't stop just by looking at the rules or by hearting the rules, or just try to practice, right, the rules. So I'm going to start with giving you a list of the rules and then take you through multiple examples thereafter. So our first rule is the constant rule. Okay, so we have the constant rule, and this basically says that d of dx of any constant k is equal to 0. Quite simple, right? D of dx, any constant k is equal to 0. So let's go into the second rule. So the second rule is the power rule. And the power rule is d of dx x to the n is equal to nx n minus 1. Okay, quite simple as well. D of dx x raised to the power n is equal to n x n minus 1. Okay, let's head into the next rule. So we're going to do the third rule, which is basically the multiplication. So multiplication by constant rule. So basically the multiplication by constant rule. So please don't mix this up. The very important word in here is constant, right? So multiplication by the constant rule, right? And this basically says that if you have to find d of dx of k, a constant k, f of x, this is basically equal to, we pull out the k, so it's k d of dx f of x. Okay, or we can write it as k f prime of x, right? These two are the same. Okay, so quite important. Then we're gonna move on to the next rule, and your next rule is the sum and difference rule. So we have the sum and difference rule, and this rule basically says if you have d of dx, that is basic d of dx of f of x plus g of x, that's equal to, I'm just gonna write it down here for more space, it's d of dx f of x plus d of dx g of x. Okay, so we split the two and we can find the derivatives of each. So that's the sum and difference rule. We're going to move on next to the product rule. So rule 5, the product rule. So this rule states that if you have d of dx and of f of x, g of x, that is basically equal to, so let me just write this down here. So that's equal to f of x d of dx g of x. So we take f of x as is, we find the derivative of g of x, plus we keep g of x as is, and we find the derivative of f of x. And we can rewrite that as basically f of x, g prime of x plus g of x, f prime of x. It's the same thing, right? If you don't want to say d of dx. So just remember, this is the product rule when you have f of x and g of x. The rule as I showed you earlier for multiplication is only if you have a constant, right? So two different rules. Then we can go into the sixth rule. So the sixth rule that we have is the quotient rule. So the quotient rule or the division rule, and it's similar to your product rule. So if we need to find d of dx of f of x, g of x, that's basically equal to, we have g of x, f prime of x minus f of x, g prime of x all over gx all squared. Okay, just take note of the way the numerator is written, right? We start with g of x and find f prime of x minus f of x, g prime of x, right? Remember, we have a minus in here, so if you mix this up, you could land yourself in trouble at the end when you're trying to simplify or do any sort of subtraction or addition. The last rule I want to show you is quite an easy one for exponential rules, right? So we have the exponential rule, and the exponential rule basically says if you have d of du, e to the u, that's basically e to the u, and then you find the derivative of u. Okay, quite simple, right? However, there is another case that you need to remember, is what if we don't have the exponential part of this, which is the e? So we'll say, what if we have d of du of a to the u? So this rule is basically we find a to the u, d of du, u ln of, or ln of a. Okay, so remember this too, right? So these are the 7 rules that I'm going to go through. However, I will give you a bonus towards the end where I will also show you the rules for trig functions as well as for logs. So let's get cracking and let's start moving into each of these rules and giving you a few examples of each. Okay, so let's get cracking. So the first example we're going to look at is for the constant rule. Quite a simple rule, right, as you've seen. So as we know, it says d by dx of any constant k is equal to 0. And we know that for any constant, if we are to draw that on the Cartesian plane, it's basically horizontal lines anywhere on the Cartesian plane. And we can see this has no slope, so it will always be 0. Okay, remember the derivative, we're looking at the slope, so no slope means that it is 0. So let's look at d of dx of 3. What is that? That's equal to 0. Even if we have d of dx of minus 1000, that's equal to 0. Okay, simple rule. Derivative of any constant is 0, and that's the reason, if you refer back to my integral video, we always ensure that we have a plus c at the end to cater for such a constant, because the derivative of it is always a 0. Okay, let's move on to the next one, which is also quite a interesting and fun one, which is the power rule. Okay, so we know that the power rule is that states that if we have d dx of x raised to the n, that's basically just equal to n x n minus 1. Quite simple once again. So if we have d dx of x raised to the 3, that's equal to 3x 3 minus 1, which is equal to 3x squared. Simple. If we have d by dx, x raised to the 5th, that's equal to 5x 5 minus 1, so n minus 1, which is just 5x raised to the 4th power. Let's look at another one and let's see if we can prove it. So if we have d by dx of x squared, that's equal to 2x. That's what the power rule is telling us, because it's basically 2 minus 1, which is just 2x. Okay, but can we prove this, right? So we know earlier on when I did introduce this topic to you, we know that the definition of a derivative is f prime of x equal to the limit as h approaches 0 of x plus h minus f of x all over h. Okay, so what is x plus h? What is f of x? We know from this example that f of x is equal to x squared. But what is f? X plus h. So fx plus h, all you need to do here is take x plus h and replace it, or place it or substitute it in the place of x. So if we do that, we have x plus h all squared. Okay, so that's taken up the place of x. So now if we look at this, we now have f prime of x is equal to the limit as h approaches 0 of x plus h all squared minus x squared all over h. And if we look at this, this is basically equal to x squared plus 2x h plus h squared minus x squared all over h. This is the limit as h approaches 0. So this is basically just x plus h all squared, because you know that a plus b all squared is basically equal to a squared plus 2ab plus b squared, right? We know that from simple algebra. So I wasn't going to show that in full, but it's quite simple. So let's continue. What do we do next, right? We know we can get rid of x squared and x squared. So now what we have is the limit as h approaches 0 of 2xh plus h squared over h. Now we're in this form, right? We need to get to the form of 2x, okay? Because that's what we're saying that the power rule is teaching us. What can we do? We can get rid of the greatest common factor, which is h. So h into 2x plus h over h. Okay, we pulled out the h from here and the h from there. Okay, now we can get rid of the h's. So this h and that h can cancel out. We now have the limit as h approaches 0 is equal to 2x plus h. So what do we do now? We can substitute for h as h approaches 0. We can actually substitute 0. So that's equal to 2x plus 0, which is basically just equal to 2x. So this is correct. We know by using the derivative definition, we are also getting 2x, and when we are using the power rule for x squared, we are also getting 2x. So that is 100% correct. So let's look at the question, or a question that says find the slope at x equals 3 for f of x equal to x squared. So as we know, we need to find the derivative of f of x, because the derivative of f of x is the slope. So let's do that. So if we know that f of x is equal to x squared, so the derivative of the f prime of x is equal to 2x using the power rule. Okay, so if we've put f prime of 3, we find that this is 2 into 3, which is equal to 6. So our slope is 6. Quite simple. So if you draw this on the Cartesian plane, we have our y and x here. We know that x squared is basically the hyperbola like this. Excuse the drawing, but we know that at x equal to 3, so let's say we have 3 here, we will have the tangent line that will pass at one point, and that slope, or m of it, is equal to 3. Sorry, 6 is equal to 6 as we calculated, right? Quite simple. Okay, so this is basically the first two rules with examples, the constant rule as well as the power rule. Next up, I'm going to take you through the multiplication of a constant rule. Alright, so let's take a look at the multiplication by a constant rule. So as we've seen, this says that dx of a constant k, f of x, is equal to, we can pull out the constant k, and then we just need to find dx of f of x, or k f of prime. Okay, quite simple, quite similar also to the integral rule, where instead of finding the derivative, we find the integral of f of x. So let's take a few examples. So let's take the example d dx 3x to the 6. So what do we do here? We take out 3 constants, so we can take out 3, and then we find d dx of x to the 6, which is equal to 3, 6. Okay, because now we are using the power rule. Okay, so we take out n, which is 6. We then say x, 6 minus 1, and that's basically equal to 3 into 6x to the 5, and we know that 3 times 6 is 24, x to the 5. Okay, let's do another one, right? So let's say we have dx of 10x to the 6. That's basically, we take out the constant, so we take out 10. We then say dx, or the derivative of 6. We need x to the 6. So this is 10. We bring out n, so n is 6. We then find n minus 1, which is 6 minus 1, and that's equal to 10 into 6x raised to the 5, and that's basically equal to 60x to the 5. Okay, quite simple, the multiplication rule, especially with its application. So let's look at the next rule that I want to take you through. So the next rule on the list is the sum and difference rule. So this rule, as we've seen, states that if you have dx of f of x plus g of x, that's basically equal to dx of f of x plus dx g of x. Okay, so let's look at a few examples. So let's say we have f of x is equal to x squared minus 9. So what do? We split this up as per the rule. We find dx of x squared minus dx of 9. Now we know with d dx of x squared we can use the power rule, and this is basically d dx of 9 is the constant rule. So doing that, we will have this equal to 2x minus 0, which is just 2x. Okay, once again, quite a simple rule. Okay, so now let's go ahead and start doing a few examples just to get our practice, and then we can move on to the rest of the rules, right? So let's take the example. We have f of x is equal to x cubed plus x squared minus x plus 2. So first step, we can use the sum and difference rule. So we can find d dx of x cubed plus d dx of x squared minus d dx of x plus d dx of 2. Now we know with these three here we can use the power rule, and there we can now use the constant rule. So this is now equal to 3x 3 minus 1 plus 2x 2 minus 1 minus 1x 1 minus 1 plus 0. Constant rule 0. So that's basically just equal to 3x squared plus 2x minus 1. Just note here, x to the 0 is basically 1, so we have minus 1 into 1, which is minus 1. Okay, so just note x to the 0 is always equal to 1. Okay, let's take another example. Let's take the example f of x is equal to x cubed plus 5x squared minus 2x plus 3. Once again, we can see we can use the sum and difference rule. So we'll find d dx of x cubed plus d dx of 5x squared minus d dx of 2x plus d dx of 3. Okay, now we can use the power rule here. We can use the constant multiplication rule here and the power rule. Once again, the constant multiplication, the power rule, and here we can use the constant rule. Okay, so quite a nice example, has quite a lot of the other rules in it. So this is basically now equal to 3x 3 minus 1 plus, we pull out 5, and then we need to find d dx of x squared minus, we pull out the 2, and now we need to find d dx of x, and we know this is equal to 0. So this is now equal to 3x squared plus 5 into 2 x raised to the 1, because we have 2 minus 1, and this is basically minus 2 into d dx of x, like we mentioned earlier, is just 1, so that remains just as 2, so it's 2 into 1. So we now have this is equal to 3x squared plus 10x minus 2. Okay, another simple and good example to look at. So quite a lot of practice with this one. Let's look at another one. So let's use another color. Let's say we're going to use green. Let's say we have f of x is equal to 5x to the 5 plus 4x to the 4 plus 3x cubed plus 2x squared plus let's make this minus 9 minus 9. Okay, and use a difference in there instead of addition. So This is quite a long polynomial. You guys might look at it and think it might be very hard, but let's use the rules and let's go for it. So let's say we now use the rules. So we have d dx. We're going to use the sum and difference rule. So it's 5x to the 5 plus d dx of 4x to the 4 plus d dx of 3x cubed plus d dx of 2x squared minus let's see if I can put this in. Can I d dx of 9? Yes, I can. So once again, we can now use the multiplication constant rule, by constant rule, the power rule, and the actual constant rule. So let's go for it. So this is basically now equal to 5 d dx of x to the 5 plus 4 d dx of x raised to the 4 plus 3 d dx of x raised to the 3 plus 2 d dx of x raised to the 2 minus, we can just use that as 0. So if we are taking this further, so we're going to have this as 5 into 5x, 5 minus 1 is 4, plus 4 into 4x, 4 minus 1 is 3, plus 3 into 3x, 3 minus 1 is 2, plus 2x, 2 minus 1 is 1. However, we missed out the 2 here, so it needs to be 2x to the 1. Okay, and now if we simplify this, this is 25x to the 4 plus 4 times 4 is 16, x cubed plus 3 times 3 is 9, x squared plus 4x. One way in which you can actually check your answer is if you look at your question up here. So if you look at your question that's up here, and if you get something like this, look at the powers, right? So you got 5 here, you got 4 here, you got 3 here, you got 2 here. And in this case, you already know you need to use the power rule, which means that the powers in your answer should be 1 less than the ones up here. So if you have 5 here, we have 4 here. We have 4 here, we need to find 1 less, so we have 3 here. You have 3 here, you have 2 in your answer, and then you have 2 up here in your question, and you finally have 1 here. Okay, so that's one way to check where that when you have a polynomial with a lot of the values in it that you need to find, checking the actual power that the x is raised to might help you, or might show you whether you made a mistake or not. So let's say, for an example, you ended up with having 4 here instead. Okay, and if you check the question, you already had a 4 here, so you know you made a mistake somewhere along the line getting this answer here. Okay, so that's one tip or trick that you can use just to check the polynomials. When you're using the power, it will be 1 less than what you had in the question itself when you're using the power rule. Okay, so let's do a question that says, what is the slope of the tangent line when x is equal to 2 for f of x is equal to 3x to the 6 plus 4x cubed plus 5x squared plus 3. So what do you think we need to do, right? So we first need to find the slope, right? So in order for us to find the slope, we need to find the derivative. So we need to find f prime of x. When we have f prime of x, then we need to find f prime of 2, because that's what they want to find. They want us to find that when x is equal to 2. So first, let's find f prime of x. So f prime of x is then equal to, we can use the addition and subtraction rule. So we have d dx of 3x squared plus d dx of 4x cubed plus d dx of 5x squared plus d dx of 3. So we have it in a familiar rule right now. So I'm going to speed this up a bit. So we're going to use the multiplication of a constant rule and the power rule. So we have here 3 into 6x, 6 minus 1, plus 4 into 3x, 3 minus 1, plus 5 into 2x, 2 minus 1, plus 0. Okay, so that's now equal to 3 times 6 is 18x to the 5 plus 4 times 3 is 12x squared plus 10x. So step 1 complete, right? So first marks are done. Now we need to use f prime of 2. So we need to find what f prime of 2 is, and that's basically 18, okay, 2 to the 5 plus 12 2 squared plus 10 into 2. Okay, so that's then equal to 18 into 2 to the 5 is 32 plus 12 to 2 squared is 4 plus 10 into 2 is already 20. So that's now equal to 576 plus 48 plus 20. Okay, 18 times 32 is 576. So if we add all of this up, we have the answer of 644. So this is your slope when x is equal to 2. Okay, so just look out for these questions. You might get something like this. They want you to find the derivative first and then solve for x. Most of your marks will go when you are trying to find the derivative, but don't lose out or don't forget to actually find the actual slope when the value is given to you. So just note for that. Cool guys, so next up I'm going to take you through a few more examples, some that you might be quite curious about. So stay tuned and we'll head on into a few more examples. Hope you're still good and still concentrating. Feel free to pause the video at any time and try out these examples, and then come back and check whether you have completed them successfully or not. Let's look at this example, right? We have f of x is equal to 1 over x. Now, if you remember in my integrals video, we can rewrite f of x as, or we can rewrite 1 over x as x to the minus 1. Now, this is in a familiar rule, so we can now use the power rule. So we can find d dx of x to the minus 1, that's basically equal to x minus 1 minus 1, minus 1 in the front here, so that's basically equal to minus x to the minus 2, and we can rewrite that the same way we changed the x. You brought the x to the minus 1. We can rewrite this as minus 1 over x squared. Okay, another simple one. Main thing you need to look at here is how can we rewrite this, right? We can get it into a familiar rule we can use. Let's look at another one. So let's say we have f of x is equal to 1 over x to the 4. So we can do the same, take the same approach here. We can rewrite f of x as x raised to the minus 4. So we now need to find the derivative of x to the minus 4. So d dx is equal to power rule here, a rule we can recognize. So it's minus 4 x to the minus 4 minus 1, and that is then just equal to minus 4 x to the minus 5, and we can rewrite this as minus 4 over x to the 5. Okay, so quite simple. Just need to recognize how we can take the question and put it into a form we can recognize and link to one of the rules. So let's say we have f of x is equal to 6 over x to the 5. Okay, quite similar to the previous one. So we can rewrite this as 6x to the minus 5. So now we know we can use the constant rule here, and we can use the power rule here. So we can now find d dx is now equal to 6 into minus 5 x minus 5 minus 1, and that is then just equal to minus 30. That's just equal to minus 30 x to the minus 6, and we can rewrite this as the previous one, minus 30 over x raised to the 6. Okay, quite a simple example again. Just change the color, but let's look at a new one, right? So let's say we have f of x is equal to the square root of x. So what do we do here, right? Like in my integral video and like in the previous example, let's get into a form we can recognize. So we can rewrite f of x is equal to the square root. We can rewrite the square root as x raised to the half. So now we have this in the power rule. So d dx is now equal to a half x to the half minus 1. Okay, and that's now just equal to a half x minus a half, and we can rewrite this as 1 over 2 x 1 over x, the square root of x. Okay, because the half is 1 over x, and because of the negative we take it to the bottom. So just to make this look neat, we can write it as 2 square root of x. Okay, quite another easy example. Just need to try to get it into a format or a view that we can link to one of the rules. So let's take a similar example. Say we have f of x, the fourth root of x to the 7. So we can rewrite f of x as the as x 7 to the 4, 7 divided by 4. Okay, so now we can use the power rule here, and by doing so we can find d dx is equal to 7 divided by 4 x 7 divided by 4 minus 1, and that's basically equal to 7 over 4. 7 over 4 minus 1 is 3 over 4, so it's x 3 to the 4, and we can rewrite this as 7 over 4, the fourth root of x cubed. Okay, so taking it back to the previous, to its original format. So let's say we have f of x is equal to x squared x to the 4 plus 7. So what do we do in this case, right? With the rules we've learned so far, we need to get into a format we can understand. So we distribute the x squared out. So we now have this equal to x to the 6. Okay, when you multiply and you add the indices, plus 7x squared. Now it's in the format that we know. We can use the summation rule here. So we now have d dx of x to the 6 plus d dx of 7x squared. Now we can use the power rules here and the multiplication by a constant rule. So we now have this equal to 6x to the 5 plus 7 into 2x squared, which is basically 6x to the 5 plus 14. This should actually be 2 minus 1, so it should just be x, so that's 14x. Okay, quite simple. Once again, get it into a format that you can recognize and be able to use one of the rules. So let's use another color. Let's say we use yellow, nice and bright. So let's say we have f of x is equal to 3x minus 5 all squared. So what do you think we do in this case, right? We need to get into a format we understand with the rules we've learned thus far. So if we take 3x minus 5 all squared, we can rewrite this as it's basically 3x minus 5 into 3x minus 5. Now if we multiply this out, we will get 3x times 3x is 9x squared. 3x minus multiplied by minus 15 is minus 15x. Minus 5 multiplied by minus 3 is minus 15x, and then minus 5 times 5 is 25. Now we can go ahead and simplify this, and we'll get this as 9x squared minus 30x plus 25. Now we can see we can use the summation rule. We can already see we can use the power rule, and then we got the constant rule right there. So let's go ahead and complete this. So we now have d dx of 9x squared minus d dx of 30x plus d dx of 25. And this is now equal to 9 into 2x, 2 minus 1, minus 30 into 1 plus 0. So our final answer here is equal to 18x minus 30. Okay, once again, getting it into a format that you can align one of the rules to. So let's take another example, right? So let's take the example where we have f of x is equal to x cubed plus 3x to the 4 plus 2x squared all over x squared. So what would you do in this case, right? Okay, we can actually rewrite this as x cubed over x squared plus 3x to the 4th all over x squared plus 2x squared over x squared. I am sure that most of you thought that we should quickly just jump into the quotient rule, which you could have done. However, this is the best approach because we haven't yet gone through some examples with the quotient rule, and when we do go through some examples, you'll actually see how different it is. So if you look at this, we can see that x squared can go into x cubed x times or 1 time, plus we can see that x squared can go into x to the 4th 2 times, so we got 3x squared, and we can see that x squared and x squared here can cancel out, so we have 2. So now it's in a format we can work with. So we can now have d dx of x plus d dx of 3x squared plus d dx of 2, and solving these derivative, this is basically 1, as I mentioned earlier, plus 3 into 2x. That's a constant, so that's plus 0. So our final answer is 1 plus 6x. Okay, so what we're going to do next is I'm going to take you through one of the bonuses I mentioned earlier, I'm going to take you through some of the trig derivatives. So get your pen and papers ready, because it will be very good for you to take these down, because a lot of lecturers that I know and that I have been through quite enjoy giving trig functions, or find the derivative of a lot of the trig functions. So get ready for the next section coming up shortly. Now let's look at the trig derivative rules, right? So let's go ahead and look at them, right? So if we have d dx of sine of x, that is equal to cos of x. Okay. If we have d dx of cos of x, that's equal to minus sine of x. Okay. Quite simple so far. Now, if we have d dx of let's take tan of x, so that's equal to sec squared x. Okay. d dx of sec of x, that's equal to sec x tan x. Okay. The derivative of cosec x, that's equal to minus cosec x cot of x. Okay. And then last but not least, the derivative of cot of x, that's equal to minus cosec squared x. Okay. So that's basically the different trig rules that you need to remember. Of course, these need to be used with the previous rules that I have shown you, as well as the upcoming rules. Let's say we get the question, prove that d dx, or the derivative of sine of x, is equal to cos of x. So as we proved earlier on, we would use the definition of a derivative, or the first principle. So we would say that d dx of sine of x, we would need to find the limit as h approaches 0 of sine of x plus h. As discussed, we make x plus h equal to whatever is it, x, right? So x is equal to x plus h minus sine of x over h. Okay, so we know that from the trig identity, sine of a plus b, that's equal to sine of a cos of b plus sine of b cos of a. Okay. I will make another video on trig identities, but if you do not know any trig identities, just remember this for now, as we'll use this to prove that the derivative of sine of x is equal to cos of x. So using that identity, we can now say this is equal to the limit as h approaches 0 of sine of x cos of h plus cos of x sine of h minus sine of x all over h. Now we can rewrite this as the limit as h approaches 0 of sine of x cos of h minus sine of x all over h plus cos of x sine of h all over h. Okay, and this, if we do take out the common factor here, which is sine of x, that will be sine of x into cos of h minus 1 all over h, plus we can rewrite this as cos of x sine of h over h. Okay, so what do we do next? So from here we can see, or we know that cos of x minus 1 can be rewritten as minus into 1 minus cos of x. So using this, we can say this is equal to the limit as h approaches 0 of sine of h over h minus sine of x into 1 minus cos of h over h. And we can pull out the cos that we had up here, and we can actually write it in the front as a constant. So that's cos. Okay, and this is now then equal to, we can see that sine of h over h as it approaches 0. So on the sine graph, as it approaches 0, we know that this will give us 1. And we know that cos will give us 0. So if we rewrite this, we'll have cos of x into 1 minus sine of x into 0, and that's equal to cos of x. So we were able to prove this. Okay, so yeah, just pay attention to this proof. You might get a few proofs in your exam or your test. This is more of the easier one that I've done. You would get a few of the harder ones if you need to use cot or secant as well. Okay, so that's it on the rules for trig. I will take you on to the product rule next, and we will combine some examples with some of the trig examples in the product rule, as well as the quotient rules, which are up next. Okay, so let's look at the product rule, right? So we do know that the product rule of the derivatives, so we have dx of f of x, g of x, that's just equal to f of x g prime of x plus g of x f prime of x. Okay, so let's look at a few examples. Let's say we have dx of x to the 4 sine of x. Okay, we can find that dx of x to the 4 is equal to 4x cubed, and the dx of sine of x, from our trig rules, we know that that's equal to cos of x, right? And we also proved it. So we can now find that dx of x to the 4 sine of x is equal to f of x, or f of x here we made it equal to x to the 4, and g of x we made it sine of x. So that's x to the 4 cos of x plus sine of x 4x cubed, that's equal to x to the 4 cos of x plus 4x cubed sine of x. Okay, so that's a product rule. Let's look at another example. So let's look at, we want to find dx of 2x to the 4 plus 6 into x squared minus 6x. So this can be our f, this can be our g. So if we're making f of x equal to 2x to the 4 plus 6, so f prime of x is then equal to 8x cubed. And if we're making g of x equal to x squared minus 6x, so g prime of x is equal to 2x minus 6. Okay, so we can now find the derivative of, so if you want to find d dx of 2x4 plus 6 into x squared minus 6, we want to use the product rule here. So that's basically equal to f of x, which is 2x to the 4 plus 6, g prime of x, which is 2x minus 6, plus we then look at f prime of x, which is 8x cubed, into our g of x, which is x squared minus 6x. So you can take this further and simplify on your own. So just simplify this and you should be good to go ahead and get your full marks, right? So I'm going to stop with this problem here because I want to look at the next one, which is a bit more interesting. So let's change the color. We also match it to be interesting. Okay, so what happens if we have d of dx f g h, the multiplication of f, g, and h? Okay, so this is basically equal to, we can go with f prime gh plus g prime fh plus h prime fg. Okay, so it's just that for each one of them we have to make sure that we find the derivative of each, right? So we found f g h. Okay, let's take an example, right? So let's take the example of d dx of x squared cot x 2x squared minus 6. Okay, so we can see that this can be f, this can be g, and this can be h. Okay, so if f is equal to x squared, f prime would be equal to 2x. If g is equal to cot of x, so g prime would be equal to, from what we learned, it's minus cosec squared x. And if h is equal to 2x squared minus 6, so h prime is equal to 4x. Okay, so now if we want to find d by dx of x squared cot x into 2x squared minus 6, that can be 2x cot of x, so we took f prime here, cot of x into 2x squared minus 6, minus, now we're going to take our g prime, which is minus cosec squared x into x squared into 2x squared minus 6, so that's your f and your h. And lastly, we take h prime, which is 4x cot of x squared, which is your f and g. So this is your answer. You can definitely simplify where we can, but I'm going to leave it there for now, and I'm going to move over to the next section where we would look at the next rule, which is the quotient rule. So now we're going to look at the quotient rule, right? So as we know, if we want to find d dx of f of x over g of x, that is basically equal to g of x, f prime of x, minus f of x, g prime of x, all over gx all squared. Okay, so quite simple. Let's look at a simple example, right? So let's say we need to find d dx of 6x plus 5 over 7x minus 7. So the first step, let's find what f of x. So we're going to make f of x equal to the numerator, which is equal to 6x plus 5. So f prime of x is equal to 6, and that means g of x is equal to 7x minus 7. So g prime of x is equal to 7. So taking this and now plugging into our rule, we now have 7x minus 7, which is our g of x, f prime of x, which is our 6, minus g of x, which is 6x plus 5, into our g prime of x, which is 7, all over 7x minus 7 all squared. So that we now have, or we can show this as we can bring 6 into 7x minus 7 minus 7 into 6x plus 5 all over 7x minus 7 all squared. So you can go ahead and simplify this. I won't be doing that right now, but you can go ahead and simplify it just to make sure you do get those extra marks. But I am going to move on to the next rule. So the next rule is the one some of us do fear, but it is the exponential rule. Okay, the exponential rule. So the exponential rule basically states that the derivative of e to the u is equal to e to the u d du of u. Okay, so let's take an example. So if we have e3 to the x, that's equal to e3 to the x d dx of 3 to the x, 3x. So that is e3 to the x. We know 3x we can use the power rule here, so we can rewrite that as just 3, which is 3x 3 to the x. Okay, quite simple, right? What if we have x to the e? So that's basically equal to x e minus 1 using the power rule. Okay, so let's look at an additional rule to the exponential rule, like we mentioned earlier on. We can have a to the u. So a to the u is basically a to the u d u of u ln of a, or ln of a. Okay, so let's take the example of d dx e x cubed. So as we say, this will be ex cubed. We then need to find d dx of x cubed, and that's basically equal to ex cubed. We can use the power rule here, so that's now 3x squared. So we can rewrite that as 3x squared e raised to the x cubed. So let's look at an example. D by dx e to the 1000. So what do you think this is, right? So if we use the rule, we know we'll have e to the 1000 d dx of 1000. And what is the derivative of a constant? It is 0. So e to the 1000 multiplied by 0 is 0. So this just proves that whenever we find the derivative of e raised to a constant, it will always be equal to 0. Okay, so you can just remember that rule as well. Let's move on to something different. So let's look at d dx of e tan of x. So that's just equal to e tan of x d by dx of tan of x. and that is equal to e tan of x. We know that derivative of tan of x is sec squared x, so we are left with sec squared x e raised to the tan of x. Okay, quite an easy example as well. Let's look at another one. Let's look at d dx 2 to the x. Okay, so this is going to take on the rule of a to the u multiplied by d du of a ln of u ln of a. So we now have 2x multiplied by 1, because d dx of x is 1 ln of 2, or ln of 2. Okay, and that's 2x ln of 2. So that's using the second rule that I showed you. So let's go with d dx, 3x cubed, that's then equal to 3x cubed d dx of x cubed ln of 3. So that is now 3x cubed multiplied by 3x squared ln of 3. And you can simplify this, right? So 3x cubed multiplied by 3x squared, you can simplify that further. So let's take one more. Let's take the d dx of 6 raised to the 3x minus x cubed. Okay, looks complicated, not that complicated. Let's use the rule au, u prime ln of a. So that's now equal to 6 raised to the 3x minus x cubed d dx of 3x minus x cubed ln of 6. So that's equal to 6 raised to the 3x minus x cubed d dx of 3x is 3 minus 3x squared, and we left with ln of 6. Okay, so that's quite simple. Now let's go into the final bonus of this video that I wanted to take you through. So that is going to be logs, right? So logs is quite important. You will get quite a few of these, right? So let's take the ln of f of x, and the rule is that's basically equal to f of x prime over f of x. What would we have if we have ln? Okay, so that's basically ln x to the k, which is a constant, so it's equal to the constant over x. Okay, let's look at some examples and you will see how this rule fits in. So if we have ln of x, that's basically equal to f prime, so x, the derivative of x is 1 all over f of x, which is x. Okay, let's take a few more examples. Let's look at ln of x cubed. That's basically equal to f of x prime, so it's 3x squared power rule over x cubed, and we can cancel that and that out, so we left with 3 over x. Okay, so try to simplify where you can. What if we have ln 3x? Okay, so we need to find the derivative of 3x, which is 3 over 3x. 3 and 3 will cancel out, so we left with 1 over x. What about this one? What if we have ln x cubed plus 1? So the derivative of x cubed plus 1 is basically 3x squared power rule here. Derivative 1 is 0, right? All over x cubed plus 1. Okay, so quite simple so far. What if we have our famous trig function? So what if we have ln of cos of x? So that will equal to we find the derivative of cos, which is minus sine of x over cos of x, and that's basically minus tan of x. Sine over cos is tan. Okay. What happens if we have the log of a constant k into u? So that's basically equal to u prime over u ln of k. So this is another rule that you need to remember, right? So let's take an example and you'll see how we use it. So let's say we have log for 3x. This should be 3x, so 3x, that is equal to our u prime. So the derivative of 3x is 3 all over u, which is 3x ln of our k here, which is in this case 4. Okay, let's take another one. Let's say we have the log of log 5x squared. That's basically 2x all over x squared ln of 5. Okay, how about another one? Let's say we have log 8 1 minus x. So first thing, take the derivative of 1 minus x, which is minus 1 all over 1 minus x ln of 8. Okay, so that's another rule you just need to remember. Okay, what happens if we, or what should we do if we have f of x is equal to x squared ln of x? Okay, what do you think we need to do here, right? So we go back to our previous rules. We would need to use the product rule, right? So we're using the product rule here. So let's make f of x, let's make f equal to x squared. So f prime is equal to 2x. Our g is equal to ln of x. So g prime is equal to 1 by x. So if we now plug this into our rule, so the dx of x squared ln of x is basically equal to x squared 1 over x plus 2x ln of x. Okay, and we can see that the x squared and the x can cancel out, so we have x plus 2x ln of x. Okay, you can take out the greatest common factor. So if we take out x, we left with x into 1 plus 2 ln of x. So just for information, if you want to simplify. Let's look at another example. What if we have f of x is equal to x squared x squared? So once again, we use product rule here. So f is equal to x squared, f prime is equal to 2x, g is equal to ex squared, so g prime is equal to ex multiplied by 2 or 2x. So plugging this back into our product formula, we would have this equal to x squared 2x plus e raised x squared multiplied by x squared. So you can simplify this further if need be, but I just wanted to show you how that is used. Okay, so what if we have another interesting example of ln of x all over x, right? So what do you think we need to do here? We need to use the quotient rule. So let's take f equal to ln of x. So f prime is equal to 1 by x. If we make g equal to x, so g prime is equal to 1. So taking this information and plugging it into the rule, we now have that this is equal to x 1 over x minus ln of x into 1 all over x squared. Okay, so this and this can cancel off, so you just have it equal to 1 minus ln of x all over x squared. Okay, so that basically takes us to the end of the derivatives and the basics of the rules. So just keep on practicing, remember the rules, write them down, keep on practicing, and you will be able to do well in your exams and your test. I will be making more videos on the trig identities as well as some more in-depth examples on derivatives, so look out for that. Also check out my previous videos on integrals, quite important as well. They do get clubbed together, integrals and derivatives.